you very much for having me today. My name is Gonzalo. I'm currently working at Gramatio Color in ETH Zurich. I'm a software engineer. My background is in software, not in geometry and architecture. So, yeah, my skill set is somewhat different from I guess others. But yeah, at ETH we're building a framework for computational design and in particular in our team for robotics. So yeah, today I would like to show you what we have and guide you through it and how to use it. Yuko, could you enable screen sharing for me? Thank you. Okay. So the session today is about COMPAS FAB. COMPAS FAB is a fabrication, like robotic fabrication package for COMPAS. But before we get started, I would ask you to go to this GitHub, to this URL, which points to a GitHub repository. You will have all the material of the session in there. The example code, the slides, if you want to follow along. So go there, and so this is the repository. And also clone it locally if you can, or download it here so that you can run the examples directly if you want. Okay. So the agenda for today, to be honest, this is the first time I do this session online. It usually takes much longer, like it's like a full day or 2 days even sometimes. So I'm gonna try to squeeze it as much as I can in a format that it's variable for an online session. I hope it's not too long or too tiring. If you have questions, if you think I'm going too fast or too slow, or things are too obvious and you want to skip, just interrupt me, please, and tell me so. So the agenda for today is like introduction to this session. Then we will go into like 101 of COMPAS. What is the COMPAS framework? An introduction into COMPAS FAB in particular. And then I will talk about robotics. There are 3 topics that I will go through. One is like fundamentals, the very basics of robotics. Then robot models and robotic backends that we use for COMPAS FAB. That will link to the next topic, which is ROS, the robotic operating system. I will do kind of a primer of ROS. I will not go so very much in deep, but it's interesting to understand the machinery that it's underneath the tools that we are using. And then I will go into the actual meat of what we want to see, like kinematics and motion planning using COMPAS FAB, using ROS and all that. Okay, so let's start. What is COMPAS? COMPAS is it's an open source framework. It's written in Python. The main goal of COMPAS is collaboration and research in architecture, engineering, and construction. It's developed here in ETH Zurich in the context of this NCCR digital fabrication program. And the driving goals, which will be, I will go a bit deeper into that, but the driving goals of COMPAS and all the packages around it is really collaboration in interdisciplinary teams and transferability, both across teams and also to the industry. So the framework is open source, but it's also open source with a very permissive license. It's MIT license, which kind of helps to transfer to industry. And it's also CAD agnostic. So whatever you build on COMPAS, you can visualize it in Rhino or in Blender, or you can, if you have a different tool, it's relatively easy to write the interface to show it in a different tool. And as I mentioned before, we will today focus actually on COMPAS FAB, which is the robotic fabrication package for COMPAS. So let's start the installation, because I asked you to prepare a few requirements for today, but I would like you, or I would like us to install it together, install actually COMPAS FAB. So if you go to the URL, this is again the same URL as before. You will be able to like copy paste from there, but if not, the installation is relatively simple. We will install from the command line. So if you're on Mac, command space and open the terminal. If you're on Windows, open the Anaconda prompt. And then the first line is only needed if you just install Anaconda for the very first time. This configures Anaconda to use the Conda Forge channel, which is the distribution channel for the community. And the second line is what we really want to do. We want to create an isolated environment to install COMPAS and COMPAS FAB. This line, just to show you in case anyone is lost, in the repository, at the end you have the same steps that I'm going through. So you can copy paste from here. You don't have to type all this. So the line that actually installs COMPAS and COMPAS FAB is this one. This is a bit longer than what you usually need. You usually just say Conda create, give it a name, and then say COMPAS FAB. But since we want to install it now while I talk, we will do all this in order to leave it installing while we move forward with the slides. So just an explanation of what this line does is, this thing is a name for your environment. It's important to create isolated environments, otherwise Python dependencies become a mess in your system. So this one will create a little kind of bubble in which all dependencies are consistent. So we give it a name, Tokyo 20. We select which Python version we want. This is optional, but since I want everyone to be on the same page, we better fix it to Python 3.8. This is what we really want to install, COMPAS FAB. We want to install the version 0.11. And this part is only needed for Macintosh. So if you're on a Mac, use this. If not, just skip it. You will see in the repository the two different versions. The only difference is that. So once you start that, it should install. It's a bit long, so we kick it off now, and then we come back to it in a while. So far, so good. Questions? Anyone that for whom this doesn't work? Should I continue?
Yes, you can continue. Thank you.
Good. Okay, so COMPAS is kind of an ecosystem, if you want to see it that way. There is a main or a core library of COMPAS, and around the core there's a bunch of additional packages that that provide domain-specific knowledge, you could say. And these packages integrate tools, and they integrate tools on like two sides of the spectrum, like backend tools and front-end tools. But at its most fundamental level, what COMPAS allows us is to write code that is focused on the core of the research and keeping the details of front-end and back-end stuff isolated from us. So COMPAS, COMPAS core, sorry, as this is a bit repetitive, but COMPAS core is open source, is an open source library written in Python. And what it contains is a bunch of flexible data structures and algorithms for research in architecture, engineering, and construction. And also contains kind of a geometry processing kernel that it's independent of CAD. On the left side of the equation, COMPAS integrates with a bunch of different backends. And what these backends are really changes based on what the package that we're using is. So in our case, in robotics, for instance, backends are ROS or VREP, for instance, and we are adding PyBullet in these days, for example. But there are also non-robotic backends like libIGL for geometry, like in interactive geometry, or CUDA or whatnot. But basically, backends are state-of-the-art tools that we don't want to reinvent. We just want to integrate into the framework. On the other side, the framework integrates with different frontends. These are usually CAD, so Blender, Rhino, Grasshopper, and whatnot. Our focus, at least at the ETH in this building, is on Rhino mostly and Grasshopper, but it's relatively simple to add other tools if someone is interested. And on top of that, we have all these packages that are domain specific. So we will focus today on FAB, the package for robotic fabrication, and kind of more specifically on the ROS backend robotic operating system. So what is really COMPAS? At its most basic level, COMPAS is really a standalone library. You can start the Python interpreter in the command line and do geometry processing, like just without visualizing or anything, just raw. It can also be used with standalone viewers like this one, but the most common use case is to use it within CAD. And this is in Rhino Mac, and this is in Blender. The important thing is that code always looks the same regardless of which frontend you're using. So this simple example of rendering a mesh, a hypermesh, shows on the left how it looks on Rhino, and on the right how it is for Blender. And the differences, if you see, the code is identical, but we will just import this artist. Artist is the component that will actually paint on the canvas of the front end. We will import it from a different package, and that's it. So, yeah. I mentioned that there are some data structures provided by COMPAS. The main ones is a network or a graph. The other one that we use all the time is a mesh, and then there's a volumetric mesh as well. There are like incrementally, over time we are adding a few more, but these remain being the main ones. And on top of that, there's plenty of algorithms to work with. Okay, but to the focus of our session, COMPAS FAB is an extension. It's written on top of COMPAS. And the goal of COMPAS FAB is to ease planning and execution of robotic fabrication processes. COMPAS FAB follows the same principles as for the core framework. So it's also open source. It's also written in Python. It's also CAD. independent, and it's also like its main goal is to provide interfaces to state-of-the-art tools in the field. In particular, because tools in the field of robotics are usually not built for to be run inside sorry, to be run inside CAD. So that's what COMPAS FAB tries to do, to bridge the parametric design environment to the tooling in the robotics field. Before moving on, how many here have experience with industrial robots, working with them? Not many? None?
Well, I don't have any. I think Yuko has.
And also Kawakami-san as Lobo.
Yes, we have, yeah. We have, Kuka です。Kuka.
So,
Okay.
so two of us. Anyone else have some industrial know-how at lab or experience?
If I'm saying something that it's unclear, so if something is unclear, just interrupt me. I might be assuming things that are not so clear for everyone, so just interrupt me. Let's go back to the installation. It should be done by now, I guess. So if the installation completed correctly, you should be able to go to, or to stay in the prompt that you are. I'm going to also do it here. And then activate the environment. Gonna activate. And then if you do pip, just to check pip show COMPAS FAB, you should see the version that is installed. So you should have version 0.11 there. Are we all on the same page? If not, again, just interrupt me. In case you haven't used Conda before, in the Conda prompt, you will see the current active environment indicated here at the beginning. And after checking the version, what we want to do is we want to make it available in Rhino, because installing it in the command line doesn't automatically make it available in Rhino. So we're going to type this line. This is also in the repository, so you can copy paste from there, but I will also do it here for completeness. We execute a Python script inside the COMPAS FAB framework where we say just install it on Rhino. This will default to Rhino 6. If you want to have it in Rhino 5, I think it's like -v 5.0, but the focus today is on Rhino 6. Okay, so that's it. And now we can continue. So 3 main areas of robotics that I want to go through today. One is fundamentals, like basics that COMPAS and COMPAS FAB add for support of robotics. Then robotic models, like how do we represent a robot in memory or in code? And robotic backends, like how do we actually get the algorithms and the code that will do all the heavy lifting for the complex stuff, because obviously not all of that is is embedded into COMPAS FAB, but COMPAS FAB is the interface to that. So fundamentals. Two concepts that are like super basic and they are from the geometry field, but we need them in robotics is frame and transformation. Each one is represented by a class of the same name in COMPAS. Frame, I guess I don't need to explain to you. The only clarification is that a frame is what Rhino calls a plane. It's the same thing. The difference is that in COMPAS there is a plane class that is that has two vectors, I think. So it's free in one axis. And then I'll move to some code slides. But before that, a quick explanation. On every code slide, you will see this thing on the top right. The number in here is the number of the example. This one matches the code in the repository. So if you have the repository open, I'm going to use Visual Studio Code because it's open source and it's pretty complete, like feature complete. You can use other editors, of course, and I just focus on one to simplify the everything. But if you go to the examples, you will see all these examples here have the same number or the number that it's referred to in here. And the two icons here indicate whether the example is meant to be run in Rhino or in some, from the command line or from your text editor or whatever, or both. In the cases where one is not runnable, and for instance, if something requires Rhino, then the other one would be kind of grayed out. Okay. First thing we will try, it's how to construct a frame. This is a bit boring, but I just need to show it so that you know what to expect. There are different ways of constructing a frame, from point and two vectors as classes, from point and two vectors as just Python list, from 3 points, from a plane, which here you see the other object in COMPAS, from Euler angles, or just some fixed ones for the origin. I'm gonna run this here just for the sake of starting to demonstrate something, but yeah, this is a bit of a boring one. I'm gonna run it in the command line here, just to be able to interact with it. I type Python, so I'm here, gonna copy paste all this first part. Okay, and then we have a frame object. If we create this one again, this frame will be almost the same. Like, actually, I think it's identical, yeah. In COMPAS, you will see this pattern possible in a lot of places. Whenever something is, some primitives are expressible either as classes, so a point as an instance of the point class, but they will also behave the same way if they are just a list of floats. So many operations in COMPAS will work with really built-in primitives rather than object instances. Yeah, okay, I'll copy all this just for completeness. Nothing spectacular, just creating frames. Okay, going back. A very important use of frame is that we can use it as a Cartesian coordinate system. So we can say, for example, this is example number 2, we can define a point as defined locally to a different coordinate frame that it's not at 0. So here we define a frame as a coordinate system, right? With this point and vectors. And we define this point as 35, 35, 35 in that local coordinate system. And then frame has two methods to transfer from world and to local. So F2 world chords of P will give you the point in the world coordinate system, and vice versa. The F2 local chords of the one that we just got will give you back the point in local coordinates. So if we run this one, it's gonna copy paste till here. Oh, sorry. So now I have P, what is P underscore and P2 and P. And then, yeah, well, we don't need to check this, but both P2 and P are the same because we move them back and forth to the world coordinate frame and then back to the local coordinate frame. We can also do it with more complex objects, of course. So moving a box into a frame, into another coordinate frame and back is the same. This one, for this example, I'm gonna jump to Rhino. I'm gonna open the Python editor here. And I'm going to open, actually, so this example number 4, you can run this part in either the Rhino or the command line. And the next one adds the visualization on Rhino. So this is only runnable on Rhino. I'm going to run that one because we want to see things. Good. So the code is more or less the same thing that we were doing with points, but here we create a box. And then we transform the origin of the box, and we visualize it with these artist things. So I'm gonna run this. This execution speed is only because it was the first time loading the framework. After that, then it's fast. And here we see we do the where is our, this is our first box in this frame, which we render. We also render the coordinate frame itself, and then the second coordinate frame over here with the box moved there. Yeah. So far, like nothing really nothing really new, but all these tools will help us with the robotics once we get there. Here we basically, like the other topic is transformations. We already seen hints of transformations when we did this frame to frame transformation, but there are also like some explicit classes for handling all the different transformations like rotation, translation, scale, reflection, projection, all these things. You can run these examples on your own. I don't think that makes too much sense to run them here. This example perhaps is just only to highlight a little thing here. What we did was transforming the origin. So we transformed the point and then we reconstructed a whole box based on a new frame. But we can also just transform the box itself. And I don't know if you're familiar with a Python convention that functions that are written in past tense will create a copy of an object, but functions that are written in present tense will just operate in place. The same thing applies to COMPAS. Objects very often have this transform function, but there's also, so there's transform and transformed, and the transformed one will give you a new object without touching the original one, and the transform will just modify it in place. We can run this one quickly. Example 14 and 15. Or we can at least open it and see the difference. You will see that I'm skipping a lot of examples. If you are interested in all the like, for instance, there's a lot of examples in the repository about transformations, different things that you can do with transformation, post and pre multiplication of transformations. There's a million things, but it's just too long to fit in this session, I think. So I'll leave them there. You can explore them on your own. Here we have this example. The example, I think, will do basically the same thing as we were seeing on the other one. The difference is how it does it. This one is literally just transforming the entire box, not creating a new box from a transform origin. The same thing applies to meshes, for example. So if you have a mesh, you will have a transform that you can pass a key, a transformation, and get the same transform results. Okay. Rotation and orientation deserve a short mention because when it comes to robot vendors, every vendor has a different way of defining rotation. So I think, for instance, ABB defines the rotation of the end effector in quaternions. KUKA robots define it in Euler angles with one set of axes. And Stolby robots define it also with Euler angles, but with a different set of axes. And URs define it as axis angle vector notation. All these different notations and ways of representing rotations are supported in COMPAS. Internally, all the transformations are represented as affine transformations of 4x4 matrices. And you know, there are all these methods to convert to and from the different representations. So finally, we're getting to actual robots. How does all this apply to robots? Well, a robot is actually nothing more than a list of frames that is chained by transformations between them. So if you think about it very abstractly, you have one frame in the world coordinate system, so the world coordinate frame, and a transformation to the base of the robot, and then a transformation from that to the first link, to the first join, sorry, and to the next one, to the next one, to the next one, till you get to the tool 0 coordinate frame, to the flange of the robot. And from there, you might have a transformation to the actual current tool, and eventually transformations from the robot coordinate frame to the object or the work object coordinate frame. You will see this, at least some of this, in particular WCF and RCF are mentioned over in several functions in COMPAS. Okay, so that takes us to the next topic, which is robot models. And how do we represent a robot in code? So a robotic arm, which is the type of robots that we mostly focus on, is a kinematic chain of rigid bodies or links that is connected by joints that provide constrained motion. These links are constrained by their connection to other links, and all so each of the joints will have one type of movement or rotation that it allows. These links connected by joints form a tree structure, and the tree structure is represented by in a text format called URDF, which you might be familiar with. URDF, I think it stands for Universal Robot Description Format or something. It's not related to the UR robots. It's just like a general UR. It's a general robot description format. It originated in the ROS project, but it's not ROS specific. There are plenty of tools that use the same format. And the nice benefit of using a standard format is that there's currently a large availability of models as open source, because like the ROS community is providing them for plenty of the robots, but in general everyone works with this, so it's easy to find these things, and when not, it's easy to build them also. So URDF has all these things. It contains the links, the joints, but it also contains the kinematic relations. It does contain some dynamics as well, but we're not focusing on dynamics in general. We will touch a little bit on dynamics towards the end when we talk about motion planning, but in general, COMPAS FAB focuses on the kinematic part of the story. So URDF more or less looks like this, which is also mirrored in the robot model of COMPAS. COMPAS.robots is the namespace or the package where the robot model is. So there's a root that represents the robot, and then there's a set of links that each one contains visual and collision meshes and primitives, and then some inertial values and a lot other stuff that it's not here. And then there's a set of joints, and those define the parent-child relationships. This here on the right is a contrived, but the smallest possible loading of a robot. And this is, of course, if you have the URDF file in your file system, you can create an instance of robot model and then say from URDF file, and it will create it. This is more or less how it looks like, but it's not that important. This I want to show again. COMPAS FAB does the same thing that COMPAS. The code is CAD agnostic or independent. So if you want to load and show a robot model, you can do it with basically the same code, and the only difference will be that the artist comes from a different location based on the place that you want to render it on. So if you run this code, you will see on each of the CADs the same robot represented. But now I would like to jump to a bit more interactive parts, because so far this is purely static. So I'm going to open Grasshopper here. I'm going to open example 25. Okay. You will see that all these grasshopper examples that we have, and also in the documentation, they don't have grasshopper components. They just have this GH component, so you can always see how the things are done. And you can always open the component and see what we're doing there. And you will notice that what we're doing there is the same thing that we have in the slides, the same code that you can run in the command line if you want. So it's rather transparent how everything is built. Okay, this example will load a robot from GitHub, if I'm not mistaken. Yeah, just we have this GitHub package mesh loader because this is such a common scenario that the robot model is packaged in a very specific format because ROS is very convention driven. So we can basically just leverage that and load it directly from GitHub. This is going to be slow because these are big meshes, and yeah, I'm just going to pull them from the internet now. This will load it. This is an easy way to get started to kind of see the robot in motion and to demonstrate this. It's not the way that you will usually load the robot because you will probably have it locally. I mean, if it's your robot, you will not load it from the internet every single time. So it will be faster. But for demo purposes, this is very good because you can run it right now in your computers and it should work. So now the robot loaded, and here we have two big blocks. One is configuration. This one is only building up a class that has all the values of the joints. It's very simple, just a few sliders combined into an instance. And this is the visualization thing that will use the artist. So if we start playing with this now, the robot moves. Yeah. As you can see here, really the code inside is very simple. Here we're building an instance of configuration from repo values. And here we will just kind of render it. This is a bit longer code because we're doing some things with colors and stuff, but in the end, the code that you want is these two lines. Like we say, okay, now update to this configuration and draw the visuals, like the visual meshes, not, so you can draw the visual meshes or the collision meshes. Robot models will always contain both because collision checking is very expensive. So you want to have simplified meshes for the collision part and more detailed ones for the visualization. Okay. But as I said, we will usually not load the robots from the internet. We will load them from a local setup. That can be just files on our computer, but the way that we usually do it is we load it from ROS because ROS will already have it loaded. So you need to configure your ROS instance to have a robot. And then we just want to say, ROS, give me the robot that you currently have. And this is how you do it. You create an instance of the ROS client and say ROS.load robot with geometry or without, and you get it. We will run this one a bit later, actually. Before, I want to mention what I briefly showed just before. There's There are two objects related to configuration stuff. There's a joint that contains joint types, for instance. The joints can be revolute, so like they rotate, or they can be prismatics, they are translations, or they can be fixed. A fixed joint is very useful. It's not really a joint, but effectively the connection between the wall and the position, the base of the robot is defined as a fixed joint because it just helps modeling it. It's the same kind of thing that you have inside the robot. So a fixed one will just have a transformation that cannot change. And based on these things, you can create a configuration. A configuration is the list of joint values or joint positions. So basically what defines where a robot is, or what position it has. There is a configuration object in COMPAS FAB that allows you to have that and pass it around. You can define it at its most basic with just passing a list of values and a list of types. You have a few helpers, but we will see later that there are other kind of helpers and ways to create configurations. Maybe one thing to highlight now is the unit systems used in COMPAS FAB is we use radians to define the degrees, like the revolute joints, for instance, and we use meters for the prismatic ones, so translational component. This is in part to match what Ross does. Yeah, this is mostly the case. Okay, so we can do a little experiment and run a code, and then you can play around with it a bit. The example is number 26. It's how you can build your own robot, because you can load URDFs from the internet, as we've seen, or from ROS, or from your file system, but you can also programmatically define your own robot if you want. So I'm going to delete this. Sorry. This one I'm going to run in Rhino in the editor. Okay. So what we have here is we are creating a cylinder as our main link. We will use this cylinder, the same cylinder for multiple links, and we will just create a very long arm, like a connection of cylinders. The next step is to create the root of the robot model. So we say robot model, we give it a name, robot. Links and joints is just empty for now. And we create the initial word link. And then we loop and create, like, add links and joints. And then we create 7 joints, 7 links. Yeah. And then we will visualize it. We can first, let me do this. So if I build this thing and then I print it, we will get some little information, like not a lot, but here we see the robot name, and then it says we have 8 links, 7 joints, 7 of them are configurable. Okay, this is expected. Now let's render it, visualize it or bake it, whatever. We're going to use the robot artist defined for Rhino again. We will start by clearing the layer in which we are putting this. And then we will define 3 things: join names that we want to configure, all the configurable ones. We are lazy here and we just say keep me all. Which values we want to put? Here is where we can play a little bit with, this is just some random value that I put times the number of joints. So it will have, all of the joints will have the same value. Types, they are all continuous. A continuous joint is more or less like a revolute, but has no limit, so you can keep rotating. And then this is how we apply that configuration. So we create a configuration instance with those joint values and types and update the artist. In the current version of COMPAS FAB, you need to pass the configuration and the joint names. In a future version, this will not be needed anymore, but for now we need this. And then we draw visuals. If we render this, we will get probably a weird looking arc, and we can play with this. These are regions, so we can define them independently, so by hand, each of them, if you want to get some other shape. One of the exercises we usually do with students doing these sessions when there's more time is like try to build your own, like build a letter or do something with the robot that shows some sort of meaning.
Hi, Gonzalo. I don't know if that's the right way to pronounce your name. Just want to understand the context of this exercise. Do we have to set up the robot every time like this when you want to use it?
No. This is only to show that you can do it if you want, that you can programmatically define one.
Right, I see.
But most of the time, you will actually just do this. You will say load the robot from ROS.
Right.
We will actually see this very soon.
So this is just for the robot setup, the robot model.
Yeah, exactly. So we're still in how do we represent robots? Like what's the model of a robot? And then immediately after that, we will jump into backends and we will see how we load them from ROS, and we will load it from ROS to see.
Okay, thank you.
Okay, so yeah, as just said, this one takes us to the third main area of COMPAS FAB, which is backends. So interface to other tools. And these other tools we refer to as backend. They really do all the heavy lifting: simulation, planning, messaging, all the real heavy calculations are outsourced to this. Because you might want to apply a different backend. For instance, we are now in the process of adding PyBullet as a backend. Because currently these are the backends that we support. We have VREP as a simulator, and we have a generic ROS integration. So by generic I mean ROS is a very large tool, and on its own, ROS doesn't do anything of robotics. It's just a message passing tool, kind of, or a coordinator. So there is a low-level integration into ROS as a backend, and then there's a slightly higher level integration into Move It, which is the most popular motion planning framework of ROS. So Move It runs inside ROS. So in that sense, you could say that we have 2.5 backends integrated. But today I will focus on ROS. ROS is super powerful. It's used by the robotic community in research and also increasingly in industry. But it's also a very complex tool. If it has a very steep learning curve. not exactly friendly to use from the environments that we are using. So not only it doesn't work inside the design environment, it doesn't even run on Windows. So it's a tricky tool to use. But it's important to understand the machinery behind the scenes of what we will do. So I will touch on some concept of ROS and why we use ROS. Main reason is that ROS is really an inter-process communication tool, and at its core. It doesn't, despite its name of robotic operating system, it's not really about robotics, and it's not an operating system. So it's neither of the things that it's in its name. It's actually middleware, and it's, as I said, it's an inter-process communication tool on top of which there's a huge community of roboticists creating robotics tools. But the fact that this inter-process communication or distributed system basically matches very closely what a fabrication process looks like, that makes it a good fit for us. So on the right, you see kind of a stereotypical fabrication process where you have a couple of robots, or 3 sensors, and a fabrication model, which probably runs in your CAD, and some design simulation that you need, especially for collision detection or path planning. And the way this would map onto ROS is kind of, you have a ROS core that is the coordinator of all these things, and all these little parts are interconnected as nodes. And the way that you can split this with ROS makes it decoupled, which is important to not end up with a mess and with a code that is unmanageable because everything depends on everything. With ROS, you are kind of forced into writing little nodes, and each node has to have one purpose, one function, and it has a well-defined way of communicating with the others, but it's not coupled to the others. So the way, to go back here, the fabrication model would be the thing that runs in your CAD, and then the simulation part is probably like either Move-It or some other path planning tool, and you have different nodes per sensor and different nodes to drive the robot, and everything is kind of coordinated with this ROS core thing. This is an example for one of our robots that runs ROS, and you see like what are the nodes. That can be anything. The important thing about a node is that it's really kind of single purpose, and it's like decoupled. So you can have, in this robot, you have a node, for instance, to drive the mobile base, and you have a different node to do the low-level control of the arm, and you have a node to do localization based on cameras, and you have a different node that actuates the end effector, for example. But nodes can be anything. You should think of ROS as a network, as a network system, as a distributed network system. And as long as a node provides a single purpose and a simplified action, that basically constitutes a node. So a node could be a driver for a UR5 robot, for instance, or it can be a connector to a camera, but it can also be a simple Python script that just prints hello world. That's also a node. It just has to be single purpose. Well, what are these nodes, or what can you put in these nodes? There's a lot of things available. ROS, again, is really large. In the whole ROS ecosystem, there's tools for everything, from the basic plumbing thing like process management and inter-process communication, low-level device drivers, then high-level tools for simulation, visualization, blogging, then all the control, planning, perception, all these things are also, you have so many packages. Sometimes it's actually overwhelming how many things you have in ROS. So one of the things we try to do is simplify that. And one important bit of ROS and why we really decided for ROS versus other things is the community. There's a huge community of ROS developers. So if you have a question and you post it online, someone will answer it. There's a good chance that someone will answer it because there's so many people working on ROS. Compared to other tools, like if you have the other backend that we support right now, VREP is pretty small. So if you have a problem there, yeah, it's harder to get support. Okay, so the last thing about ROS, and I don't want to, yeah, as I said, ROS is very complex and we could be spending an entire semester talking about ROS, but we just want to use it as a tool, not to be experts in ROS. But there are three important concepts in ROS communication. You can create a node that it's a topic. You can create a node that it's a service, or you can create actions. These three main ways of communication are fundamental to everything. A topic is a unidirectional, it's a one-way data stream. So for example, you have a sensor and that sensor will just push data into the system. You just send data. You don't care about who's listening. As a topic publisher, you just send data. So it basically follows a publish and subscribe model where the publisher doesn't need to know about the subscribers, and yeah, as long as data types match, then it's all fine. Then the other type of communication is services. Services are blocking. They follow the request and response model. So you ask for something and you expect the other side of the equation to respond, and it should be a kind of a short trigger or calculation. So for instance, calculate the path or open the gripper, something that will take a finite amount of time and not a lot. Of course, sometimes path planning is slow, but that doesn't make it not a service. Because in opposition, you have actions which are similar, but they are kind of a mix between the two. They are non-blocking. So you ask for something, and instead of getting the control back when the action is over, what you get back is a token to either cancel the action or to get the results. So for example, if you do navigation, you say, now robot, you have to go there. This can take an infinite amount of time because the operator can pause the execution, but as long as it's somehow resumable, actually it will end at some point. So you don't want to be blocking, you want to just basically get a token to get the goal once it's completed. Examples of this: navigation, execution of motion. Now, how do we get ROS? As I mentioned before, ROS is a Linux tool. There's like, you will actually, if you Google, you will probably find references to, okay, now ROS runs on Windows, but that's almost a lie, I would say, because as I was saying, ROS at its core, it's not about robotics. It's only about inter-process communication. And everything about robotics is additional packages. When you see that ROS runs on Windows, what they actually mean is that the inter-process communication part of ROS runs on Windows, but none of the packages that you want actually run on Windows. So currently, ROS doesn't really run on Windows for our use case. So we need to be able to run it. And the way that we do it is with Docker. I don't know if you're familiar with Docker, but Docker is somewhat like a virtual machine thing, but it's lightweight. So imagine that you have a Python script that you want to distribute. The Python script is like super tiny. It's less than 1 kilobyte. But you want to make sure that this is really reproducible and it runs the exact same everywhere. If you put it in a virtual machine and you want to send it to someone, you can do that, but it's probably going to be like 5 gigabytes or 2 gigabytes of virtual machine with a Linux OS in there, and it will take 30 seconds or 1 minute to start, and it will be very slow. What Docker does is it removes the operating system from the equation. So you can put code that runs on something that for the code, it looks like it's in a virtual machine, but it's not. It actually uses your operating system and just emulates the guest operating system, which means that the virtual machine, the Docker images can be very small, and you can actually distribute something as small as a little Python script in a container, because it will start instantaneously. The startup time of a Docker container is almost it's really instantaneous almost. And they basically give us reproducible entire systems that we can pass around. So that turns the whole ROS installation, which is very complex, it basically boils it down to either this command on the command line or this thing from Visual Studio. Again, I'm mentioning Visual Studio Code because it's very convenient, as indicated in the requirements. If you have these extensions installed for Docker and Python, you can do this super quick. So what I'm going to do now, and what I would ask you to do as well, is we're going to start ROS on your systems. And we're going to start it with one robot that we will use for demoing. So this thing is in the repository that you cloned or copied or download. If you go to the Docker folder, you will see this Docker compose file. And here you see how we define like which services of ROS we want. And then if I say, can kill this. If I say right click compose app, this will start everything. It will start the ROS core. It will start a ROS bridge, which is the thing that we use to be able to talk to ROS from the design environment. It will start this ROS file server, which is the thing that will basically serve the meshes that we need to load a robot model. It starts also a UR demo that has motion planning in there, so move it for a UR5 robot. And it will also start the GUI. Now, Docker usually doesn't have a graphics interface. So now we have this 1, 2, 5 containers running, but we don't see anything. They already started, so what you saw here is starting up ROS in a Windows computer. If you go here, you can see what you have running on your system. So we have all this, but we don't have a UI. So what we did was in the README, or in the main README, but also in the slides, once we started, we can go to this URL I'm going to copy it from somewhere here. Yeah. This URL is going to your own computer, right? So this is kind of a window into what happens inside these containers. And here we have the robot already loaded. This is Move It, the motion planner, and this visualization toolkit is called RVs. But here we could already start planning inside ROS directly. But if we do something like this, then we can plan something. Okay. This is good so that it helps you understand what's going on. But we will not need it too much because we want to use it from the code and from Rhino and from other environments. So it's good to know that it's there, but we don't need it for now. One important detail: if you could not install Docker desktop and instead you install Docker toolkit, which is the older version, then instead of localhost, you will have some URL like this. This one shows up when you start Docker toolkit. I'm trying to not use toolkit if possible, but if you don't have Windows Professional, you might need to. But also, yeah, what happens is that if you don't have Windows Professional, the emulation of this whole thing, it actually happens in one virtual machine. So you end up with one IP address to funnel into the whole world of ROS. Okay, before I move forward, did everyone manage to load this and see the robot in the browser? Or how are we with that?
Yeah, I can see the robot in the browser. How is everybody? Daijoubu desu ka, minasan? 今のところで、あれ、もしもし、大丈夫ですかね。サムアップあるんで。It looks okay.
Looks okay?
Yeah, everybody looks okay.
Good.
Yep.
Cool. Okay. Then so if anyone else has problems, just remember to interrupt me, please. Now that we have ROS running, we can run a few other examples. So I'm going to go. The basic thing that we will do is just verify that the connection works. Again, if you have Docker Toolbox, you always need to change this localhost thing for the IP address that toolkit gives you. But assuming not, then I'm going to go to this example, check connection, which is very boring, but we just say ROS client. We create a new instance of ROS client. I don't know if you're familiar with the with construct in Python, but this one is only a way of ensuring that we clean up the resources correctly. So this one connects and disconnects properly. It's more or less the same thing as writing it like this. So we can put the connection in a try catch or in a try except block, and then we can say client connect. run, and then this, and then accept, and to remember disconnect, or finally, actually, this is what we want. So we want to disconnect always, even if there's an exception. But it's much easier to do it with this with syntax, because then it really takes care of all the details of like cases failing, code failing, or whatever, and then it will just close the connection. So we run this one, just very simplistic check. Run it. Okay, so we have a connection. Not very magical. So let's do something a little bit more interesting. I mentioned that ROS is a distributed system tool. That means that we can easily talk to different nodes, so different processes, without having to do any coordination, any threading, any synchronization of queues or things like that. We can just create a different topics, and they can talk to each other. So the canonical example of ROS is two nodes that talk. Like one is a listener and the other one is a talker node, and they just send messages to each other. So the talker is basically a publisher node. There are 3 steps involved in doing something like that. First one is connecting, which we just did in the previous example. We use the ROS client from the COMPAS FAB backends. Then we need to advertise a topic. This is just saying, hey ROS, I'm here and I'm going to start messaging you with messages on this inbox or topic name and for this type. Types actually deserve a longer mention, and there's and ROS is a strongly typed language or framework, so that means that everything actually needs to comply to types. In Python, we don't see any of that. Mostly, all the types are lost. Well, not entirely lost, but they are not checked. But we need to make sure that what the data we send is convertible to the data types that ROS demands, because otherwise it will just not go through. So we say, I just want to send strings in the slash messages topic. This is the topic name. And yeah, advertises the start of that. And then it's rather easy. We just say talker.publish, and then we send a dictionary. Here you see that I said I was going to send strings, but I'm sending a dictionary. And that's because even the string, even the primitive data types are actually complex message types in ROS. So these ones actually mean that you have a dictionary with data, and the data is of type string. Same thing happens for integers, floats, everything else. And that there's a lot of more complex message types available. Of course, you can also define your own if you want. Defining your own is easy, but we will not go through that. So that's the talker node. It will just publish, and then we have this little loop that will wait and send, wait and send. So I'm going to run this in two completely detached things, so that you can really see that they are completely disconnected. Here I have one command line, and I'm going to run example. This is 28 plus Docker. Okay, it started sending, so it disconnected and sending. And now we want to subscribe to that. The other end, so the listener node, we want to subscribe to a topic. The code is similar. We connect to it first, and then we subscribe. And subscribe here, it's a bit different, the syntax. You see that the topic instance is the same. So client messages the topic name and type. But here, instead of advertising, we say subscribe, and we pass a function. That function will be.
Can
Yep.
I interrupt? Sorry to interrupt. I still have some problem with the example file for 27. It says failed to connect to ROS, but I'm not sure what I should do for that.
Okay. Do you have Visual Studio Code?
Yes.
Yeah. If you did you do compose app on this Docker compose file?
No, I didn't do that.
Okay. Then try that one, and let's see if that fixes it.
Okay. Should I just right click to anywhere in Docker Compose?
Yes, either in the file itself or here in the main window, and you should have this compose up.
Yeah. Okay.
If everything goes well, then it should say done, 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 and then it should.
Yeah, it's downloading something.
Okay, if it's downloading, it will take a few minutes or.
Okay, so I'll check it right after it's all done. Thank you for showing.
If it doesn't, then raise your hand.
Okay.
Interrupt without problem.
Thank you.
No worries. Okay, so here, what we do is we subscribe and pass a function. That function it's a callback that will be called every time there's a new message. So we say, the function is very simple. Here we say receive message, we'll take one parameter, one argument, it's message, and we're going to print. And we're going to print the data, since we saw that the actual content of the message should be a dictionary that has a data property with hello, which is printed. And then, and then at the end there's just a slip, just to wait in there. So I have this window open still, it's sending stuff. And I'm going to go to another window. I'm going to use my VS Code window. I can open another command prompt, actually. Anything will do. And then I'm going to run example, I think it's 29. So Python, CL29, listener, and good. So we have messages. So what we see here is that this process is talking to this process, and we didn't have to write any complex networking code or anything. So if we stop this guy here, and this one will also stop hearing, and yeah, good. So inter-process communication works. So we can move to the real purpose of why we're doing all this, to do robot planning and kinematics and all these things. So far we've been working with the robot model alone. The robot model is part of COMPAS core. It describes the kinematic change, linkage, geometry, and this sort of things. But in COMPAS FAB, we need a few more things. So there is a robot class that that composes. So it includes the robot model inside. So you create an instance of robot based on a robot model. So planning. I'm going to focus on Move It because this is the one that we mostly work with currently. And there are three main building blocks involved in planning. There's kinematics, which it's either inverse or forward kinematics. These are the functions that will allow us to map between the joint space and the Cartesian space of the robot. Then there is motion planning, which is perhaps the most interesting part. There are two types of motion planning modes. One is Cartesian, that is kind of linear in tool space, and the other one is kinematic or just free space planning, just getting from A to B. And the last topic is planning scene and planning scene operations. So what we want to do is basically where we want to get is here. This is what we see here is Move It, integrated into Rhino. And this one is doing all the operations that that I just mentioned. This one is doing a Cartesian plan to pick up the brick because it needs to be like the tool needs to linearly move down and then up. Then it does a free space motion planning to get to the position in which it will, to the approach vector basically. And then it does another Cartesian plan to do the final step of insertion. And in between all the planning scene operations that basically attach the brick to the robot, then detach it once it's in place and add it to the scene so that the build wall appears. And then it's taken into account for collision checking. So this is what we want to eventually get to, or what COMPAS FAB actually allows you to do. Let's start with kinematics. As I mentioned, an industrial robot can be controlled in two spaces. One is joint space, and the other one is Cartesian space. And to put it in very rough terms, we use two kinematic functions, the forward kinematic and the inverse kinematic function, to transform between those spaces. So if you have a Cartesian frame and you want to get which are the joint values of that robot model that will get you to that frame, you use inverse kinematics. And the opposite is true. If you have a set of joint values and you want to go from that configuration space and you want to get which one is the frame at the end effector, then you use forward kinematics to go back to Cartesian space. I detail or I make a note on a note on inverse kinematics or IK. The analytic solution for 6-axis robots returns usually like a fixed number of 8 inverse kinematic solutions for any robot. These are so this depends on the limits, of course. So if one of the joints can rotate multiple times, there are more, but I think they're kind of nominally 8 because then plus all the rotations that you can have. If you have more more than 6 axes, then the situation is different, and then you can have redundant joints, basically. So finally, we get to the meat of the situation. How do we get forward and inverse kinematics from a robot? So once we've seen all the things that we've seen, then this part is very easy. We have a robot instance, and then we have forward kinematic function that takes a configuration. We have seen how the configuration is built before. We have seen how to load the robot, and we will see how to load it again in an example. And let me just say, get me the config for this, get me the frame for this configuration, and then we can, these are like described in more like spec mode. The input is always the configuration, the output is a frame, defining work coordinate frame. This is important to highlight, and that's it. Forward kinematics can be executed by COMPAS FAB in memory or by move it. You can choose, but you don't even have to. By default, it will do it in memory because it's faster. But you can also say, I really want move it to give me the forward kinematics solution. This is example number 30. We can run it. I'm going to run this one in Visual Studio Code, because then we're going to move to Grasshopper and see it more visually, but for now. So after all this lengthy introduction into robotics, I think it's nice to finally get to a point in which getting the real values that we want is simple. So this is the full example to get forward kinematics. And here in this basically 4 lines of code, what we do is we connect to ROS, to the ROS that we started with Docker Compose up. We load the entire robot that it's loaded in ROS. This is the UR5 robot. We define a configuration, an arbitrary one, and we ask, okay, robot, give me the end effector frame in work coordinate frame for this configuration. And that's what we get. So remember, this is in meters. Yeah, so the output is in meters. Okay. Now, inverse kinematics is also simple. The operation is reversed, so it takes as the input the frame in work coordinate system, and it outputs a configuration. So I just mentioned before that the analytic solvers return 8 configurations for IK, for inverse kinematics. However, ROS is not, or at least doesn't have by default that one configured, so it returns only 1. And if you want to get multiple, you have to seed it with a different init configuration or start configuration. Oh, sorry, this line is incorrect. This is 0 configuration, not init configuration. I think the code is correct. Yeah, 0 configuration. So inverse kinematics will get the configuration. We'll get 1 configuration that we can use to reach this frame based on the start configuration. If you want to get more, you need to kind of feed it different start configurations. In principle, though, if you pass the 0 configuration, it's randomized, so you get a random one every time you call it. So let's run it. It can also happen that it doesn't find anything. In that case, it will complain because all the planners that we'll use are stochastic, so there's a chance that it doesn't work. Okay, now it did. So we got a configuration. Yeah, if you see this configuration, I'm gonna open these two things because they, when I run the forward kinematics, it returned this frame, see, like 03, 01, 05. Now I'm running inverse kinematics for the same frame. And you would kind of expect to get the same configuration, but we're not going to get the same, and at least not always. Sometimes we might, but if I run it again, I might get another one. Could be the same, but could also be a different one. So there are a total of 8. Yeah, we got the same one. Okay, now we have yet another one, but it's also not the one that we passed here. So if we keep trying, we will eventually get to this one. Good. So that is inverse and forward kinematics. And now we need motion planning. Why do we need motion planning? Well, for two things. Like one is collisions. Like we don't want to collide with the wall, of course. The other one is trajectory checking. So maybe you want to synchronize how two robots move so that they can move together, or consider the moving objects in the scene, and yeah, for instance, these are two example projects that we had. The one on the right is one of the earliest, or perhaps the first one that we did in the large robotic fabrication lab at ETH. The one on the left is interesting. This one requires a lot of planning because the robots are working very close to each other, and it's very movements are very intricate to get there. So even though it doesn't look very complex, it's actually most of the positions are hard to reach if you take into account the other robot and the little space that they had to maneuver. And for continuous processes, you can also use trajectory. Okay, details. Big difference between the two modes of planning: Cartesian motion and free space motion planning. Cartesian is linear in tool space, so the tool will remain, like a frame of a tool will remain the same throughout the mode. Free space motion is how to get from A to B. So you define a frame, a starting frame and an end frame, and you let the robot do whatever. As long as it doesn't collide, it can do whatever it wants. So how do we do each of these? Again, luckily this is also simplified by all the work that we've done so far. So doing a calculating a Cartesian plan is basically a matter of passing a list of frames that we want to pass it through. So it can be maybe have a curve and you want to discretize it and then pass through all the points, or however you define. Maybe it's just 2 frames. In this example, it's just 2 frames go from here to here, but it will keep the orientation. Again, here, this is a mistake. An older version of the site, this should be 0 configuration as a start config. And that's it. The Cartesian planner of MoveIt is not super smart, to be honest. It tries its best, but it's basically just iteratively calculating IK solutions until it cannot find anything. So it's not a super elaborate planner. We can run it here. Okay, so we managed to find a partition path with 25 configurations. It follows 100% of the trajectory. This is something that it's somewhat yeah, I personally find it a bit annoying. ROS can return a Cartesian path that it's incomplete. Because of the way the planner works, it can return without an error, but it's not complete. It didn't manage to get to the end of your requested path. So there is this fraction thing in the trajectory that will tell you if it managed to find everything or not. And there is also an estimation of the time it would take, because even though our focus in COMPAS FAB is on the kinematic part of it, so we care about, like, the difference between path planning and motion planning is that path planning will only care about the geometry in a way. So these are the configurations, the list of configurations that we want to get through. But motion planning will also include values for like acceleration, velocities, effort, and other like dynamics. The motion planning includes dynamics. And since it assumes a bunch of things, and then it can tell you how long it will take to execute. This is not very visual. We have here a slightly more visual thing of the same code. We are going to calculate the path and then show the trajectory in the command line. This is using matplotlib, so it should be installed with the installation that we did. But okay, so the output is this one. So it charts the changes in the position. So this is each of the axes, and then the velocities usually follow this trapezoidal-ish thingy, and accelerations, you see it goes a bit crazy. Okay, one thing to highlight here is the output of the planning functions is always a joint trajectory, and a joint trajectory is basically just a list of configurations. It has more information. It has timing information, like this dynamics thing. But again, we focus on the fact that this is a list of configurations. Okay, and then kinematic motion. This is how to get from A to B, regardless of intermediate steps, just not colliding. It's basically the same thing as the Cartesian one, with one difference is that we are not passing a list of frames. We are passing a starting configuration and a set of constraints that it needs to follow. Now, the constraints, you can define very complex constraints, but we're going to focus on a simple one, that it's a goal constraint, like a position constraint. Sorry, not goal constraint, a frame constraint. We're going to say, robot, please build me the constraints based on frame. Because the constraints are actually tricky to really construct. You can also do that by hand, but this is a shorthand that is very convenient. You say, I define a frame and some tolerance in the position and in the axis, in the rotation. And you just ask the robot to build a set of constraints, a list of constraints. And then we can say robot.plan motion with that. Again, we always need this start configuration. In this case, I'm not using the init, the zero configuration. I'm just explicitly saying you should start from this, because that will always, most likely, it will be the case that you want to start from somewhere and you want to get somewhere. This is not like the IK stuff. Okay, so we run it. The planner that we use, here we are selecting a planner. This is RRT, rapid, something like rapidly exploring random trees or something like that. It's the algorithm. These are, there's a list of different algorithms that you can use. In practice, we found RRT or SBL to be the most consistent ones. SBL tends to give nicer paths as a result, but it's slower, and RRT is fast, and sometimes it gives like super random results. They work, but they are very, very strange sometimes. Okay, so it found a kinematic path with 22 configurations. It takes almost 3 seconds to execute if we were to run it in a robot. We can do the same, we can run the same thing with this little visualization of the trajectory. So here we see we got a different one. This one has 45 steps or configurations, and it takes 5.5 seconds to execute. You see how the positions change, the velocities also change very weirdly, but yeah, this will get there. A word about constraints. You can actually define constraints. You can define joint constraints, orientation constraints, and position constraints. And those can actually be defined for the goal and also for the path. So you can say that during the whole path, this constraint should be obeyed. So the more you constrain the planner, the harder it will be to find a path, of course. Yeah, this probably has it. So yeah, as I said, ROS planners are using stochastic. They are stochastic planners. So the output is not optimized for any criteria except spectacularity or drama, maybe. Sometimes you get things like they will swing the robot all over the place just to get there. But it gets there. Okay, and last bit, we're approaching the end of the session. Last bit is planning scene operations. So far, we've only operated with the robot in kind of in vacuum. There's nothing in a planning scene, but there is an easy way to define what is on the scene. There's a planning scene object in COMPAS FAB that will that has methods to add collision meshes, so stuff to the meshes to the world, to the planning scene, remove them, append, and the service mentioned, appending a collision mesh is kind of grouping. Say, for example, that you're adding bricks to a wall. You don't want to have to name every single brick, for instance, because collision meshes have a name, but you don't want to name 13,000 bricks, for example. So you just want to say these are bricks, and they go to the group of bricks. So you append to a name bricks, and then when you remove bricks, all of them will be removed in one go. So it's just grouping. And then there is this. So these are collision meshes in the scene, and these are attached collision meshes. So things that are attached to the robot. They can be attached to the end effector, like a tool, or a beam that you're moving, or a brick or something. But they can also be attached anywhere else. So maybe there's a backpack attached to a joint on the robot, to the link of the robot, or yeah. And again, add and remove. We have some examples here, but I'm not going through them too much because I want to jump to Grasshopper directly. You can also play them on your own. But I want to go to example 38. which is a combination of everything we have seen today in one gigantic grasshopper file. So okay. So this is a demo grasshopper file for COMPAS FAB. You have the loading of robots here, the connection to ROS here, and you can set tools, add meshes to the scene, rather simply all of that. Here there's a big panel with information that is just to show things. And over here we will see the 4 topics that we have seen. Like this is forward kinematics, inverse kinematics, Cartesian motion, and kinematic motion. They are all available here, and then the visualization part. So I'm going to start with visualizing forward kinematics, and I'm going to load the robot that we have in ROS. This is all set to load the robot in ROS. If you're using Docker Toolkit, you will need to change the initialization of the ROS client with the IP address of your Docker Toolkit. If not, you can press here. This will take a few seconds anyway, especially with Zoom taking up all my resources in this computer. Okay, while this one loads, how is it going for everyone else so far? Does it work in general for you?
I cannot load the robots.
Sorry, I didn't.
Yeah, I couldn't load the robot when I press the load button. It doesn't. I have the error. Yeah.
Okay. Were you able to connect to ROS when we did the connection test?
Yes, I think so. It was working. And
Okay.
the client, the ROS client is working. The second one, below the ROS button, the ROS client.
It shouldn't take that long. Mm. Hello, back.
Hello, sorry, the connection was off.
Hello, Dad. Hello, Dad. Dad, hello, Dad. Hello. Hello. Hello, Dad. Hello. 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 Hello, Dad. Hello.
Is
Hello.
everyone working?
Hello.
Hello, hello, hello.
Hello.
How much does it usually take when I press the load robot button? I think I'm waiting like a minute, but still
Yeah.
it freezes up.
No, usually, yeah, it usually takes a few seconds, not long. But here it also froze in my machine. Let me restart.
In the first example, loading a robot was working, but just this one is not working. The first one, first grasshopper one, the example. Example 25. 25 is working. Loading a robot is working. 38 example doesn't load robot.
Yeah, I killed grasshopper right now, and I'm restarting it. And I'm going to stop my video for 1 second. I keep the audio open, and just in case it's really, because Zoom kills my resources. Let me see.
Mom.
どなたか動きましたか？ちょっと私の方で動かない感じなんですけど。
もうフリーズしております。
Still frozen?
Everybody's frozen. I don't know, because the Zoom thing or the connection.
I was playing with this one last night, so it should work. Check if there's anything strange here, but it all looks good. No, this definitely shouldn't take this long. Okay, here we go again. Let's try something else. Okay, connection works. Okay. Okay. Well, I don't know if I did something wrong last night, but I now tried disabling this before loading, and then once it's loaded, I think it's fast. And let me re-enable all this. Okay. Good. Okay, I will need to check why that happens. But if you want to follow, just disable all these blocks, load it, and then re-enable them. What I did here was I first connected to ROS client and then loaded the robot. I don't have the tool selected, but I do have a mesh. The meshes are internalized, so you should also have them here. And there's a little mesh there. I can show you here. In this case, it's good to have this browser viewer, because you can compare that the thing that you see is actually what gets to the other side. So we have the same mesh, and then I can attach a tool. Attaching a tool here is just selecting one. So here I just plugged one mesh that is internalized here, but you get like if you want to have multiple tools, you can attach them to this component and then select it with this one. These bits actually show how to convert a Rhino mesh to a COMPAS mesh, which is just a one-liner. You say Rhino mesh from geometry of the Rhino mesh to COMPAS. So we have this COMPAS meshes here. We have the tool now attached. See this little block thingy, whatever, I don't know what it's supposed to do. Then information, whatever, just information, a bunch of information. And we are now visualizing, we have various modes of visualizing. We are visualizing the forward kinematics solution or the direct manipulation of configuration. We can also see the inverse, and the tube planning things, which we don't have resolved yet. So for forward kinematics, we have these things to manipulate. This is the same as the ones we had before when we did the example, what is 25, I think. This one just manipulates the road here. We are using the in-memory one, so we don't call move it for this. So yeah, nothing super fancy. Now let's go for IK. IK is a bit more interesting. You can define IK. This is the IK component as, again, everything is Python, so you can always open it and see how it's done. The code, besides all the noise of checking stuff and keeping it in Grasshopper stickies, the code that really does the inverse kinematics is the same one that we have seen. So we call robot.inverse kinematics for a goal frame. But since we want to define the goal frame easily from Rhino side, I have a little sphere, so I can take it to manipulate it. So now this one is my sphere. I will set it. So now I can okay. So now if I move this little sphere, the robot will move finding a configuration. This so the sphere also allows me to change the orientation, of course. Okay, here it didn't find a configuration that works. Okay, this one's to work. What happens every time I move the sphere is that we go to ROS, calculate the IK, come back, update the model, and then update the visualization. Good. Let's try Cartesian paths. For the Cartesian path, I have this curve. Like, this is a very simplistic thing, but you can define in any way you like the Cartesian path. And I have this curve, I have like dividing it in discrete planes and kind of creating planes out of it. So once I have all these planes, I can compute the Cartesian motion. Again, this one calls the same function that we have seen before, robot.plan Cartesian motion. This is using more parameters, more of the optional parameters. It's not only saying frames and start configuration, but also defines a maximum step between the solutions, whether to avoid collisions or not. Yes, we want to avoid collisions. And then if we have attached collision meshes, this is basically the tool that we have attached. So if I compute here, hopefully we get a path. Okay, it worked. You see, fraction is 1, so we got 100% of the path. These are all the same charts that we were seeing in the visualization thing in Matplotlib. So this little slider here will allow me to walk through all the trajectory. If you see how the end effector stays always in the same orientation, it's this is the constraint of the Cartesian thing, right? That you want to move linearly in Cartesian space of the end effector, right? Also in tool space. But if you explore the output a little bit, you will see that all these things, Cartesian and the other one, they are always outputting a list of configurations. You know? So if we see the response, we can play a little bit with this thing here. Just print it. Response is a trajectory object, a joint trajectory object, sorry, that has points, also has a few other details, but has points. So you can see this is a list of 22 points or configurations. If we check the first one, you will see that this is a joint trajectory point. Joint trajectory point is an object that inherits from configuration. It has the same things plus the dynamics. So it has accelerations and accelerations, I think it is. I don't remember. Yeah. And efforts or effort. Yeah. And also the position or the joint positions in radians. Good. And then if we move to the last one, the motion planning thing, here I also use the spheres. I'm going to bake them as well. And this guy is the starting one. Okay. I'm going to switch the visualization to see my kinematic plan. So between these two spheres, I want to calculate a path. Oh, that didn't work. You saw the red blinking. Okay. Maybe I will move this a little bit. Perhaps it's this one. if we see something here, so we see the robot here, means that the inverse kinematics of the starting one worked. So it probably means that the other one is not reachable somehow. Okay, now we got the result. We have our positions, velocities, and accelerations. And if we go through this thing, okay, it's very weird, but yeah, sometimes it does these things. As I said, these are stochastic planners, so they do whatever they want. Yeah, okay, not so bad. Okay, yeah, that's actually the core of what I wanted to show you today. Did it work for you in the end? Did you manage to load and play with this, or it's frozen?
Yes, it worked. As you explained, I have disabled all the other components first and run the robot, and then it worked.
Cool. When I was talking, I remember that one of the last things I changed last night was this thing that does IK a few times. So perhaps I actually screw it up a little bit in this example, and yeah, this one should have something like if it's connected. I guess this one just tries to get IK immediately. Yeah, this is probably not connected, and then it's hanging here forever. Yeah, but good that it works now. So since it's already quite a long time, I'm going to wrap up this part here, and then we can discuss if you want. Just want to mention a few words about like what happens next, because we have now, we can path plan things. So what do we do with this plan? How can we send it to the robot, right? So there are three ways of sending to the robot, like offline control, online real-time control, and online non-real-time control. We focus on the last one, online but non-real-time. Real-time as it's defined for the roboticist, you know, real-time as hard guarantees about the real-time, about the execution times of certain things. So not in the sense that you cannot control it in live, the robot, that you can do, but you don't have a super strong guarantee that no instruction will take more than, I don't know, 0.03 milliseconds, because it's in a loop of whatever hertz. So and the offline control mode is just you generate a script out of the paths that we created and upload it to the robot. The online real-time control, like the difference between real and non-real time will come from the driver that we use. ROS, and in particular the ROS industrial project that produces a lot of the drivers for the industrial robots that we use, is not consistent about that. Some drivers are real-time, some drivers are non-real-time. Depends. Like the ABB driver that exists on ROS industrial is an uploading driver or a downloading driver that's not real time, so you need to upload the entire trajectory before it can execute, which is not very useful. But then, for example, the UR driver is real time. It basically means that the UR driver replaces the control box in a way. It does all the calculations internally. It's a closed loop, controlling the servos at the servo level, not a script controlling motion at like move L, move J level. But we're focused on the last one, and for that we developed our own driver for APBs. which is not yet open source, but we are trying to open source it very soon. What I can tell you already is that even though it's not yet open source, it is freely available for academic purposes. So if you have any academic usage that needs an ABB driver, just get in touch with us. It's free to use. So yeah, once we have the trajectory and we have set up the driver that we want to use, then the execution is simple. The robot client has two functions, either execute join trajectory, which is a high-level interface that goes through the move it pipeline, or robot client that follow join trajectory. It's very similar, but it's slightly lower level. And you get a wait token as a result. So this one executes immediately. Your code can keep working, and you only block once if you call wait on result. Otherwise, you can let the robot execute and your Python code continues to work. This already mentioned. Yeah. One thing is, whenever some drivers, like not all the drivers have a unified interface, but you can always use the ROS client and topic services, as we have seen today with the publisher listener, so Docker listener example. You can always access all of them using this slightly lower level integration. And then a word about what is next for us. COMPAS FAB we will release a new version of COMPAS FAB soon, 0.12, I think. That has a few interesting things, especially PyBullet integration, so that you can do a lot of the things that ROS does without having ROS. So you would not need Docker, for instance, for some of these operations. There's also a new architecture for extensibility of backends. So because we want to spend much more time integrating new backends, so we refactor things in a way that it's easier for us and for everyone else, actually. So one of the backends that will hopefully be integrated soon is a PyCoreo from the MIT guys. It's a guy, I think his name, I don't know if I will pronounce it correctly, but it's Yiyang Huang. He's an MIT researcher, and he built a Cartesian planner that it's not based on ROS, that is very good. And then the other thing is this is our internal driver, the one that I mentioned, the ABB driver. It's version 1 already. And again, if you have used academic usages, actually any non-commercial usage is free to use. So just get in touch. Yeah, that's it. That was a lot of talking. Sorry. I hope you like it.